So we just finished proving a theorem on yesterday, this theorem of Marchior and Polverenti from the 90s with refinements more recently, which establishes a connection between solutions of the Euler equation on R2, with for which the initial data has the vorticity concentrated in a bunch of balls of radius epsilon around points who are bounded away from each other by distance order 1. So a connection between the Euler equation with initial data of this sort and the so-called point vortex ODEs. And so we've shown that in some sense, the point vortex ODEs really actually describe the motion of concentrated approximately point vortices in the two Euler equations. And so we started discussing very quickly how to modify this theorem for the case of bounded domains. And right. And so let me let's continue that discussion. And so the Euler equations on a bounded domain. Well, we typically impose this this boundary condition here would be the boundary condition. And so the first order of business was to modify the Biot-Savart law to accommodate the boundary domain with this boundary data, which we talked about how to do. And so we had this modified Biot-Savart kernel, K, which was the old Biot-Savart kernel, the one on R2. And then we add a piece who is found by, so for every y, we solve Laplace's equation. We find a harmonic function in the x variable whose boundary data depends on y. Okay, and so this is a correction who guarantee, and so this K of x comma y, if we think of it as a function of x for y fixed, this would be the velocity field at a point x generated by a sort of a unit of vorticity at the point y. And then this correction guarantees, among other things, that this velocity field will be tangent along the boundary, which we require. Okay, and so then having said this, well, we predict a law of motion for the vortices, which was we have this velocity field, and so each point vortex generates. We can give it as having two contributions: a singular part, the part with the 1 over distance from the vortex behavior and purely rotational, and a regular part. And so we think that for a given vortex, the singular part that it generates will not affect its own motion, but everything else does. And so then its motion will be given by the contributions of all the other vortices plus the regular part of the flow generated by itself. This was our prediction. And the theorem we stated was a precise analog of the previous theorem. I didn't recall the total statement. With so now I consider the Euler equations on the bounded domain with these natural boundary conditions, and the ODE is modified by this in the way we discussed. Okay, and so let me quickly describe how to do this. And what we'll do is we'll look at the previous proof. Well, okay, so here's the starting point. So let's remember how we proved the old the last theorem. So we spent a lot of time considering the Euler equations in with a Lipschitz background flow, Lipschitz continuous background flow. And so that's the, and so we rewrote the Euler equations as a system. Essentially, we took the initial vorticity had these m blobs. And so we wrote this system where omega epsilon m, little m is what happens to the mth blob as it evolves in time. Okay, so we look separately at the contributions from all these different blobs. And so each one evolves by, there's a piece u epsilon m, which is the velocity field generated by that blob itself, and then the f epsilon m is the velocity field generated by all the other guys. And okay, and so so here, however, when we talk about the velocity field generator, we have this more complicated law where we have both the, well, this term, the x minus y perp over x minus y squared, and then the other term reflecting the presence of the boundary. And so what I'll do here is I'll consider for the mth blob, I'll consider this piece to be only the singular part. Only the part generated by the with the the kernel that diverges. That okay, it's singular, but it's perfectly symmetric. And so in the F epsilon M, I'll put the contributions from all the other vortices, that's here, so the sum over all other L. And this is the same as what we elsewhere called K of X and Y. The contribution from all the other vortices, the velocity field generated by all the other vortices, or rather all the other vortex blobs. And then the regular part of the velocity field generated by the mth blob itself. Okay, and so this is our new system, our new way of splitting the equations. And now I'm just going to repeat the previous arguments, basically. And so let's go back and look at them. I'll just point out where we have to change things. So here they were. Okay, so the starting point was to write the order equations of the system. We've done this in a slightly different way. So this has changed, it's changed a bit. But note that the U is, this part is really the same. This is the same as before. We're really just considering the convolution with this radial, this perfectly symmetric singular kernel. And then it's the F who's changed. And the F, so the idea is, well, the F is changed, but the F is totally smooth. So we really don't have to worry about it very much. Okay, so what did we do? We said, we defined sometime capital T with the property that, or say T epsilon, I believe was what we called it, such that up to time T, we fixed time capital T, and we said up to time capital T, all the points in the classical trajectories, the ODE solutions, remain a distance delta away from each other. And so if we look at balls of radius delta over 4 around those points, well, those will be bounded away from each other by some distance delta over 2. So it's a number that may be small, but it's fixed. Okay, so we look at these balls of radius delta over 2 around the points. And so first we argue that the velocity fields F epsilon M, say the relevant velocity field in the mth ball is Lipschitz continuous, at least in the mth ball. And so this goes, and so here, okay, the definition of F is a bit different, but this goes pretty much as before. And so the point is, well, so in the new F, we have these, the same singular contributions as before. So we've just added some smooth stuff. We have the same grad perp of x minus y over x minus y squared coming from the other blobs. And then we have these h of xy. All of those are totally smooth as long as we stay away from the boundary. And I guess I should have said here, I fix a time t epsilon such that up to time t epsilon, both the vortices are distance delta away from each other, and also their distance delta away from the boundary. So that would be one modification. And then having done that, I can argue as before, because I just added on some smooth terms, that the background flow for the mth blob is Lipschitz continuous with some constant who I can estimate in principle up to time t epsilon. Okay, so this will be, okay, so we modify it, but basically we know how to do that. We can figure that out. So here was the definition of t epsilon, and I would have to add another condition. The distance of the support away from the boundary of the domain is at least delta, say. Or rather, I guess in the definition, so here I fixed. So here I would say the distance of Pm of t from the boundary of this is bigger than delta for every m and for every t. Okay, good. And so then we verify Lipschitz continuity. Then we quote the previous, and so the point is we have these previous theorems analyzing the order equations of the background flow on R2. And here's one of them that says we can track the center of vorticity and the concentration around the center of vorticity in a kind of a certain L2 sense. And the second one is that the support of the vorticity doesn't grow too much. We can control the growth of the support of vorticity. And the point is, in all these theorems, when we consider this equation, the U is the one found by the so this is the Biot-Savart law on all of R2. But that's the same U we're using in our decomposition. And so we can just quote these theorems because of the way I've chosen to split, to put the singular but symmetric part here and everything else there. Okay, I can just quote these theorems once I have Lipschitz continuity. And so we get conclusions as before. We get, for example, the support, we control the support of the, well, in fact, down here, we have these different things. And so P epsilon m was the center of vorticity of the mth blob. Capital P epsilon was the trajectory found by looking at by following the background flow in the mth blob. And then we want to, and our main remaining task was to compare this P epsilon m, the background flow in the mth blob, to the flow given by the point vortex system. And we did that down here. So we had to compare the background flow in the mth blob to the background flow given by the point vortex system, which is written here. And the idea was that, well, again, we had to look at these kinds of quantities. And so here we'll do the same thing, except we have extra contributions from the part of the kernel reflecting the presence of the boundary from the distant blobs, and then there's also a part from the mth blob interacting with itself via the boundary. But all that stuff again is smooth, and so if you do complicated, I mean, slightly more complicated estimates, not much harder, we get things in the same form. And so we can see, okay, there are details to check, but we can see the philosophy of the proof goes through, or should go through, with no difficulty. Okay, and so that's all I want to say about this, and this is partly a review. And so in the end, what we did is we found that if I look at the difference between the trajectory found by solving the point vortex ODEs and the trajectory found by following the background flow in the blobs, then we can control the rate of growth of that thing by essentially by itself. Okay, there was a factor, a small power of epsilon added on. And so once we do this, then just by ODE arguments, by so-called Grunwald's inequality, we can control, we can find that we get bounds of this, which are, say, we can show that for times up to some power of epsilon, a little bit smaller than half, we have uniform bounds, uniform in T. Okay, and that was and that allows us to finish the proof. This was true as long as we're considering time as less than time T epsilon, but this allowed us to say that in fact T epsilon is the time capital T we started with, the time on which we wanted to prove the validity of the theorem. Okay, and so and so we can see pretty much the same argument would work. And that's all I wanted to say about this for now, about the 2D point vortices. And so our goal then was to go on to the next topic, which is, and so in short, things are kind of the same, and I've gone over it, partly because when we discuss the Gross-Piatkowski equations later on, we'll consider a bounded domain. There it's much more convenient. And so I'd like to have a clearer, have the theorem in the same setting. And also just as sort of a quick review to go over the proof one more time to see, to help solidify it in our memories. Okay, and so the next thing I want to discuss, which will take us several weeks, is so topics related to vortex rings, by which I mean, in effect, the 3D order equations with cylindrical symmetry. And so, as I said, this phenomenon of so-called leapfrogging of vortices is, you can think of it, I mean, if you like, you can call it a 150-year-old open problem. It was first mentioned, at least in a qualitative way, by Helmholtz in the paper in 1858. And it attracted interest throughout the 19th century and early 20th century. But any rigorous proof of this is so far a bit too hard for anyone to do. of the open problems I'll mention, I would say the prominent open problems I'll mention this semester, this is the one who is least out of reach, I would say. So let me remark, I recently came across an interesting, so Helmholtz is always credited as being the first person to introduce the study. I mean, he used to initiate the rigorous study of vorticity and fluid dynamics. So he formed the notion of vorticity and wrote this beautiful and justly famous paper in which he derived the equation for the evolution of vorticity in Euler flows, proved things like the vortices convect with the flow. He studied point vortex dynamics. In fact, the theorem we just proved, he talked about it in a qualitative way. And he also discussed this this leapfrogging again in a qualitative fashion and just a single vortex ring translating. Let me remark, although Helmholtz is credited as being the first to initiate the study of vortices and fluid flows, there are actually a lot of papers. I recently came across a very interesting historical paper who made the point that there are a number of, say, empirical papers predating Helmholtz, and so they didn't have much theory, but they had observations of vortices. And these date back to the 16th or 17th century in contexts like, well, some volcanoes emit things that look like vortex rings. These were observed, or so there's some chemical reactions that were carried out in the 18th century. And then smoke rings was a famous example. So the study of vorticity really became, I mean, at least these empirical accounts of vorticity started appearing in literature at the same time smoking appeared in the West. And let's see. And actually, apparently there's a book written in the mid 19th century about tobacco, its history and its uses. And the author remarks in passing that in German universities, very complicated tricks involving smoke rings where students spend a lot of time mastering these tricks of sending one smoke ring through another and so on. And so, and the author of the article, having quoted this, notes that it's not impossible that Helmholtz himself as a student was playing with smoke rings and that stimulated his interest in vorticity. So anyway, this is the next topic I want to discuss, and I don't know if I have any more. I think, okay, so we're going to go to, we'll go to here. I need a few more pages. Okay, and so for me, the study of vortex rings means the study of the Euler equations for in the certain symmetry class, and so what's called axisymmetric flows without swirl. And so let's have some notation. So for the next half hour or so, I'm going to denote vectors with an arrow on top, as we do when we're teaching calculus classes. And so so let's say E sub j, for j being 1, are the standard basis vectors in R3. And let's say then that E R and E theta and E Z are the corresponding basis vectors for cylindrical coordinates. So Ez is just E3. Er we can write as x1 over R E1 plus x2 over R E2. And E theta is minus x2 over R E1 plus x1 over R E2. Okay, and here R, as usual, is x1 squared plus x2 squared to the 1/2. And in general, we'll have R and theta and Z will correspond to the point R cos theta, R sin theta, and Z. Okay, and so when I say axisymmetric without swirl, let me see, I need to do something. Axisymmetric without swirl means I'm considering vorticity, I'm considering velocity fields of a certain form with a certain symmetry. And let's So, so axisymmetric without swirl means we look for a vector u, a solution of the Euler equations, which has the form, say, u r times e r plus uz. Let's see if I can. Times e z. Okay, and so this is distinct from general flow in two ways. These components depend only on r and z, and there's no theta component. If I had also a u theta of r z times e theta, this would be called axisymmetric with swirl. And so that's so without swirl, it refers to the absence of that component. Okay, good. And so the natural domain is, so here's more notation. And so, of course, when I consider the Euler equations, these will all be functions of time as well. I just didn't write the t variable. The notation is, I'll say, maybe h is the half plane. So this is the natural domain of these functions. Okay. Okay, so then continuing, okay, and so then I want to write the equations in terms of u, r, and u, z. And so it's easy to check that if u and say p is the pressure, if these solve Euler in R3 and u has the above form, then u without an arrow, so the reason for the arrows was to distinguish them from the stuff I'm about right now, u, r, and u, z, and p solve. Well, one thing is that, okay, so I'll write this, it has the same, okay, in fact, it's the same equation. So here u dot nabla is the ur component times ddr plus the uz component times ddz. And gradient of p is, so p is a function of only r and z. It doesn't depend on the theta variable, naturally. And the equation is the same. There is one change, however, and that's the incompatibility condition. And so when you compute when we write down the incompatibility condition for the vector u in R3, we find and we express it in terms of the u r and the u theta. It becomes 1 over r, the divergence of r times u is equal to 0. Okay, so that's the only change. And so this is on the half plane h, and the natural, say, boundary conditions are the r component is 0 on the boundary of h. In other words, well, that's the R component is the, so the boundary conditions where R is equal to 0, the R component is the normal component. U dot unit normal is equal to 0. I've just written this twice. This is natural. So we're used to thinking this saying you can't flow through the boundary. That's what it would mean in RFV. It means something different here. And so let's look back up at the at this. I can see if little u, if u, r, and u, z are continuous functions, then this is just a requirement of continuity on the boundary. So in other words, if UR is non-zero, if UR is positive, say, let's imagine for convergence the UR and UZ are both positive, then the vector points toward the first quadrant, say. Then along the Z-axis, I have this vector field who is always pointing outward like this. But as I rotate around, it's always pointing radially outward, and so this would be quite badly discontinuous. So this isn't a no-flux condition. This is a regularity condition. If I want smooth solutions, then I need this. And if I have only functions in a solo space, this still is some kind of a weak. I would understand this as trace sense, and it would still be some sort of weak continuity condition. Okay, so this is the natural boundary condition. Okay, let's. I don't know when I grew so fond of this purple color. So, okay, great. And so that's the equations we'll study. And so for me, when we talk about vortex rings means this equation, the Euler equation for axisymmetric flow without swirl. I want to study that equation, and I want to consider the kind of initial data or the kind of solutions we looked at for the Euler equation on the plane. In other words, I might look for, say, solutions revolved by some kind of rigid motion. So the simplest one would be, I think we've seen videos of these vortex rings moving in R3. That would correspond to a point in the RZ half plane who moves with uniform velocity, or a point or a blob of vorticity concentrated in a neighborhood point who moves with uniform vorticity. Or else I might consider initial data a number of points in the half plane, and then I look at small balls around. I consider initial data concentrated in those things, and I ask how does the solution evolve? And a good enough answer to that question would constitute a mathematical proof of the existence of this leapfrogging phenomenon that we have seen, and so that's still absent. So that's not an easy question. Okay, and so again. Vortex rings means studying, at least in this class, for Euler means studying these equations for the kinds of solutions we considered before. Okay, and so what I want to do now is I'd like to consider basic properties of let's call this star. In fact, I want to consider of a more general equation of a more general equation because it's often of interest, and I think it helps to discuss things in a bit. It helps with understanding, at least initially, to discuss this in greater generality. And so this equation is, I'll write it here. It has also the first, the first equation is going to be again the Euler equation with no change, and the second equation will be, say, 1 over b of x times the divergence of b of x u is 0, and so this will be in. And so I should say h cross some time interval. And so let me consider for d in R2. We could do this in other in higher dimensions if we wish, but R2 is natural and it's all we'll ever consider. So here B is a function from this domain D into a non-negative function, and it's given, it's fixed, and maybe we can imagine it being C1, smooth, whatever. So in our example, D is the half plane, and B of R comma Z is just R. Okay, and so okay, and so I'll consider the same boundary conditions. And let's put these in that color. Okay, and so this is an obvious generalization of the previous equation, just the Euler equation with a weird form of the divergence-free condition, with the divergence-free condition having a weight. And okay, so let me actually call this equation star. Okay, and so let me see. Let me remark, where does this come from? With star may come from. Well, okay, so we got our one version of it by taking Euler in R3 and making a kind of ansatz and doing a sort of a symmetry reduction. And different versions of this can arise. Different symmetry reductions of Euler can give rise to different forms of star. For example, I can take Euler equations in higher dimensions and assume more complicated symmetries, and that would give rise to, for example, so a symmetry reduction. Of Euler in Rn for, say, any n with, more complicated symmetries. Okay, I don't know if we'll ever talk about this, but there's something called there's a kind of symmetry I like to call biaxial symmetry, and this would give rise to this equation star in the in a quadrant in the quarter plane with a weight who looks like, if I call these components x and y, it would look like x to a power p and y to a power q, where p and q are both integers, in fact. And so that's a form of that would be one way of getting this equation star. And this is of interest, well, to me and a few other people at least, for reasons that we may or may not talk about. And the other is, in fact, star is called the lake equations. And so what it does is, in that interpretation, you have a domain D, so a domain in the plane representing the surface of a lake, of a body of water. We imagine that it's a body of water filled with the inviscid incompressible fluid as described by the Euler equations. And we imagine that the depth is small compared to the horizontal dimensions of the lake. And so think of B as being let's write it informally. D is like a lake, and B is like the depth. And I would do some kind of rescaling, and so the actual depth is maybe epsilon times b, and I take a limit and something like that. And then say u at x is I take the horizontal components. So I imagine that in fact the water is moving around in the lake in some way that involves both horizontal motion and then vertical motion. And but I only care about the horizontal motion. The vertical motion is internal to it. So it's the horizontal components of the fluid velocity. And then I average from 0 to b of x, and then I divide by b of x. So it's I look at the horizontal components and I average them. And there's some derivation that says that you can pass from Euler to this so lovely equation. And so that has a different derivation. Anyway, so it's been studied especially for the second reason. Okay, and so B, I believe, stands for bathymetry, which is apparently means something like depth. Okay, so hence the letter B. Okay, and so then let's look at basic properties. Okay, so there's some basic properties, and so in particular, our interest is applying these in the case of the axis symmetry without swirl. But one could, so every question will ask, could also be asked about these more general versions of the equation star. So the Lake equation, where typically you would take the domain D be bounded. That's kind of natural, and you might take the depth B to go to 0 on the boundary. If otherwise there's a sort of a cliff, an underwater cliff at the edge of the lake. And even that's kind of hard. That's so these questions have been studied, but not there are many open questions. Or in the other situation, the symmetry reduction, the natural setting is, say, a quarter plane with these very concrete weights, powers of the distance from the two axes. But all of these questions are largely open. There's some results of the Lake equations. Okay, so then, so the basic properties I have in mind, well, are, what's the analog of vorticity transport that we have for the Euler equations, or what's the analog of conservation energy, or who knows what, all these properties. And so let's start to derive them. And so, vorticity transport. So let's see. So we have the equation u sub t plus u dot grad u plus grad p is 0. So I apply so the definition of vorticity is I take the orthogonal gradient and I let it act on the velocity u. And I call that vorticity. And so this will give me an equation for omega. And I'll get a term where there's a omega sub t. And then I'll get a term where I have a u dot this. So when I differentiate this thing, I'll get that'll just turn into an omega. And then when I differentiate this, you have to do a bit more work, but you end up getting the vorticity times the divergence of u. And then, of course, the orthogonal gradient of a gradient is 0. Okay, so a short computation is needed to get this term from differentiating that. Okay, and then, so far I haven't used the funny divergence, the funny incompressibility condition. Let's do that. So we know that here's the incompressibility. And so this tells me that the divergence of u is, I think, minus the gradient of b dot u over b, right? So the gradient of b dot u is b times the divergence of u. So I rewrite that. I put that into here, and I find that, well, omega sub t plus u dot grad omega minus u dot grad b over b times omega is 0. And if I look at this, this should be I'm going to write something down and then we'll see if it's correct. Okay, and what I've written here is just the so-called material derivative that we're used to seeing. So this is d omega dt. It's the derivative along particle trajectories. Okay, let's see if this is correct. So when I differentiate this, I'll get a term involving u dot grad omega over b. That's this. So I divide. I'll divide this equation by b. So I'll get a u dot grad omega over b, and I'll get a term involving minus. I get this term. I'll get a minus b to the minus 2 times gradient of b. Okay, so and so we know that. So what this tells us is that the thing that's, sorry, ddt, this was a terrible typo. The material derivative of the vorticity divided by the weight b is, this says that that's convected by the flow. So in other words, if we define, so I'll define, so we're reviewing stuff here. If we define the particle trajectory map, you know, I can't, okay, there's a, I don't know how long this question has been here. Okay, let's go. So I thought there was a question, but there isn't. Okay, so then let me see. So if we define the particle trajectory map as usual, dx dt is u of x of alpha t and x of alpha 0 is alpha. Then this says exactly that d dt of omega over b along these trajectories is 0, because what happens if if I differentiate, I'll get a term involving d omega dt, and I'll get a term involving the gradient of omega, the dot product with dx dt, which is exactly u. And so, and b, of course, is independent of time. Okay, and so omega over b at the point x of alpha and t is omega over b at alpha and 0, and I need a okay, and so basically everything can look like the order equations, except there'll be little changes here and there. Okay, and so that's the first thing. The second, let's look at this. Right. Okay, good. So let me rewrite this. So let me multiply by b. Again, dbt is 0, so I can just I can bring that outside the derivative, and I can write d omega dt is bu, the dot product with the gradient of omega over b. Rewrite d omega dt plus bu dot the gradient of omega over b. This is 0, and this is, and I can just write this as the divergence of bu times omega over b. I've made a mistake, let me fix that. Okay, but this is 0 because that's the incompatibility condition. So what does this say? D omega dt plus the divergence of u omega is 0. So I'm looking for things like conserved quantities that we have for Euler. And so the first thing is the vorticity is transported by the flow. I like that. The next thing is that the vorticity actually is also a the time derivative of the vorticity is a divergence, and so the integral over the domain of this is the integral over the domain of the divergence of u omega, and omega u dot nu, and this is 0 because this vanishes. Okay, I should be careful if. So my domain is not all of R2. It's always it should have a boundary someplace, but it may still be unbounded. Maybe a quadrant or a half plane. And in that case, I need sufficient decay at infinity to justify this. And so we'll have to check that more carefully. But at least formally, this integral of omega is conserved. What else? Also, and I should have put t here. Omega of xt dx is constant, independent of time. Solution. Okay, next. Another nice property of the Euler equations, which we actually barely used so far, but it's at least nice in principle, is conservation of energy. So next, and so what we see is everything's modified by the presence of a weight. Well, almost everything. This one wasn't, but let's look at the. So it'll turn out that the energy, the relevant energy, is going to be like this. Okay, so the if I look at the time derivative of this, I'll have, so b is independent of time, u dot u sub t. This is b u dot, and then what was it? It was okay, there's a minus sign, u dot grad u plus grad p, and I'll just rewrite this a bit. This is the right. I believe this is what we get. And so if I carry, it's the ones, if I differentiate this, if I carry this differentiation here, when I differentiate, when I take the divergence, I get 0. And so I just take the divergence of the other term, and it ends up, and one ends up being able to rewrite this. It's not. Yeah, so that will be u dot grad u. And then we have a gradient of p here. So, so again, any negative parts as before. So as before, the time derivative of the integral of over d of b u squared dx is, it's the integral of the boundary of the norm of the dot product of the unit normal with this thing, and the vectorial part of that is exactly this u here, and so I get a u dot nu, and that is equal to 0 by assumption, and so So this quantity too is constant, and that's conservation energy. Okay, and so what I want to go on to say is that so all of this is completely general. What happens? I mean, so the axisymmetric Euler equations without swirl have two good properties that distinguish it from this general equation star. One is there's one more conserved quantity, there's an extra conserved quantity, and the other is we can write down the Bios of R, the correct analog of the Bios of R formula in a rather explicit form. And so we'll make use of those in our analysis of vortex rings.